Well, hello, class. This is Mr. Roberts at Shasta High School, and we're going to go over the study team test for Chapter 2. Just a reminder, CP has completed Chapter 1 and the Appendix A, and we've completed Chapter 2, and we're now pretty far into Chapter 3. This test is the study team test, which is kind of a practice test, a look at the types of things we should be able to do competently when we take our individual test for Chapter 2. This was given the previous week, and the test is this week. I realize that that means nothing to you, depending on when you're watching this video, but let's go ahead and start and go through theirs. The first thing it says, I want to remind you this, is show work to earn partial credit, right? Credit, partial credit. So if you have done a problem and you're missing some small detail, and I can see that small detail in your work, you can get 2 out of 3 or 3 out of 4 points, right? If it's a 3-point or 4-point question. But if there's nothing there, just a wrong answer, I have nothing to do except all I can do is just subtract the full 2 points or 3 points or 4 points. So please show your work. The first question is very straightforward, I think, right? And it just requires us to remember that we can write a line in the form y equals mx plus b. Any line, with the exception of vertical lines, we can write in this format. M, you remember, is our parameter, or it's our slope parameter, and b is our parameter. It is our y-intercept parameter. And once those are set, right, we're talking about a particular line. Well, they said that we're going to have a slope of 3, and they said that we're going to have a y-intercept of 5. So with those two values clearly identified, we can write the equation of the line. It is simply y is equal to 3 times x and then plus the number 5. So that has the requisite y-intercept and it has the requisite slope. Next question. It says, hey, this line has a slope of 3/4 and it goes through the point 8, 10. So this time we're not given the y-intercept, but we are given a point that the line goes through. And what we do is we use that point, and we'll identify the x value and the y value from that point, and we are given the slope, right? We know that that's m, and we're just going to plug what we know into this form of a linear equation, right? The slope-intercept form of a linear equation. So I'll write down as a reference for us, y is m times x plus b. For our given point, the y value was 10, and the intercept was 3/4. I'm sorry, the slope was 3/4, and the x value was 8, and then plus b. So we're just looking at 3/4 times 8 plus b. If I look at this, right, 8 is 8 over 1. So I look at this and I see, hey, that's 2 times 3, which is 6, right? I know that 8 divided by 4 is 2 times 3 is 6. So this is 10 is equal to 6 plus b. But maybe for some reason you don't understand fractions that way. That's a problem, right? I encourage you to don't feel weird about it. If you're not sure how to get that value, use your calculator. So I'm just going to type 3/4. There's our fraction, 3 over 4. And I'm just going to multiply it by 8. And again, I should hit times 8, times 8. And again, I can see that that's going to be 3 times 8 is 24 divided by 4, which is 6, or 8 divided by 4, which is 2, times 3, which is also 6. So no matter what, it says that that's 6. So you can see that we've got our 6 there. And now in order to figure out what b is, I'm just going to take 6 away from both sides of this equation. 10 minus 6 is 4. And 6 plus b minus 6 is going to be just b. So we have the two parameters we need to know, right? We've got our slope parameter, m, and we have our y-intercept parameter. So we can write the equation of this line. It is y is equal to 3/4 times x plus the number 4. And we should write that in both places over here also, right? So I'll write y is equal to 3/4 x plus the number 4. All right, next question. It says this line goes through points A and B. And you can see it, and fairly straightforward. If I was to create a slope triangle, I can see that from point A, I've got a rise of 1 and a run of 1, 2, 3, right? So I know that this slope is 1 over 3, or 1/3. So our slope is 1/3. And if I go down 1 and backwards 1, 2, 3, I can see, yeah, I really am hitting the value 2, right? I don't want to assume that I'm hitting that, but I'm clearly hitting that because I just followed that slope pattern back. So I know also my y-intercept is at 2. So I have both parameters, so I can write the equation of the line. The equation of the line is y is equal to 1/3, there's our slope parameter, times x plus 2, which is our y-intercept parameter. Last problem, you're given a table of values, and for this table of values, we are asked to figure out, hey, what's the equation line that passes through those points? Now, if I take any one of these values, for example, if I take the number 16, I can take this 16 and just subtract the value that preceded it. 16 minus 10 is 6, so that grew by 6. 22 minus 16, that looks like 6 also, right? So I can see every single time I step forward, right, this is growing by 6. So I was trying to show the subtraction, but let's be clear. This grew by 6, this grew by 6. And as those numbers are growing by 6, notice what's happening to our x values. They're just growing by 1, right? So again, the slope, remember, is the change in our y values, right? And here I can see here's a change of y value that's equal to 6, divided by the change in the x value, and I can see that change in x value is 1. So slope is delta y over delta x. We're looking at 6 divided by 1, so our slope here is 6. Now, one of the things we don't see is x is 0 listed in the table. If it was, we would clearly see our y-intercept, but we don't have that. So what we have to do again is figure out what our y-intercept would be. So we're going to use our slope, which is 6, and one of these points, and it doesn't matter which one at all, I'll use the last one. And I'm just going to write, here's our y value. Again, y is slope parameter m times x plus y-intercept parameter. We know this x is 8, and the y that goes with it is 28. So I'm going to write 28 is my slope parameter 6 times 8, and then plus b. And I'll subtract 6 times 8 from both sides. So 28 minus 6 times 8 is b. And if you're arithmetic phobic, right, just please evaluate this. 28 minus 5 times 6, 5 times 6. And you can see, not 5 times 6, 6 times 8. 28 minus 6 times 8, that would be a nightmare. Boop. Okay, so I've got 28 minus 6 times 8, 48, is the number negative 20. So my y-intercept parameter is negative 20. Now, we're going to do two things, though. Before we move on, I want to write down the equation. Y is 6 times x minus 20. But I want to show you, again, how we can check these values using our calculator. So I'm going to grab my calculator. I'll just clear it and hit table. And I'm going to enter this function, which is what? It's 6 times x and then minus 20. And I'll press enter. I'm going to set my table to start at 0, step by 1, and I'll just go with auto. So it'll just generate a bunch of values. Boop. And I can see, first of all, lovely. Notice when x is 0, I do have a y-intercept at negative 20. That's great. If I go down to the number 5, when x is 5, I should see 10, 3, 4, 5. Yep. 6 should give me 16, 22, and 28. So I can see I've got great confirmation that this is indeed the equation that will use these values of x and generate these values of y. It's the line. It's the line. So let's go ahead and write it down. Y is 6 times x and then plus, nope, not plus, it was minus 20. Minus the number 20. All right, next, we're asked to do two problems where we are given the input of a function and we're asked to evaluate or find the output for that value input. So a suggestion, right? I'm going to go ahead and take and write this. Here's the first parentheses. I'm just copying this, and I've got a 3 times my input. My input is the number 3, so I'm going to put another 3 in here. So that's, you can see that's the input that just made it in. 3 times 3 plus 1 more, close parentheses, open parentheses. Here's a 3 for my input, and then plus 2, close parens. So this first set of parentheses is 9 plus 1, right? 9 plus 1, which is the number 10. So I've got 10. I'm going to be multiplying that by 3 plus 2, which is 5. And when I multiply that, I get the number 50. So when x is the number 3, this function produces an output of 50. So we'll just say, hey, this is the number 50. That's super. Next one. This problem really illustrates why it's important to be judicious in our use of parentheses here. So I'm going to go ahead and say, hey, here is a place for the input value. And the input that we're given that x is the number -4. So I'm going to write this -4. We're going to square that, and then we're going to increase that by 4 more. And here's kind of the problem. If we're not careful with this and we're using our calculator, we can clearly get the wrong answer, right? This is showing that the value -4 is what needs to be squared. So when I use my parentheses, it correctly gives me an answer of 16, which is what -4 times -4 is, plus 4 more, and then I get 20 here. However, if I was to just hit -4 and then square that, notice this is literally the opposite of whatever 4 squared is. So it's going to give me -16. So we could easily get this problem wrong if we're not aware of that. So be careful. Be aware of what you are squaring. In this case, we are squaring x. And what is x? X is -4. So we've got to make sure that the -4 gets squared. It's a -4 times a -4. And the parentheses matter here a great deal. So the answer is the number 20. Next page. Here we see kind of the other side of this coin, right? What's happening now is it says, hey, identify the input that will produce the given output. So now the question is, what input would I put into this function to get an output of 80? And in order to answer that question, all we're going to do is take the definition of this input, right? This function, rather, the function f of x, which is 4 times x plus 2 times the quantity of x minus 20. And we're going to set that equal to our desired output. So I'm setting the definition equal to the output and just solving for x. So I've got here 4x plus 2x minus 40, and that equals the number 80. 4x and 2 more x's is 6x minus 40 is 80. Add 40 to both sides. 6 times x is 120. And if I divide both sides of that by 6, I believe I get 20. So x is the number 20. Now, of course, it's a nice idea to go ahead and check that. And I guess I'll use my calculator to check it. So I'm just going to go 4 times 20. And then I'm going to add to that plus 2 times open paren 20 minus 20, which is clearly going to be 0. And guess what? 4 times 20 is 80. So hooray, 20 is the value that makes that true. Again, set the definition, right? The definition of the function equal to the desired output. And when you do that, solve for x, and it'll tell you this is the input, right? When I give this thing 20, it's going to give me the number 80. Another one like that, this one right here, this is very straightforward, right? So again, my input, I need to find. My desired output is 17, and I'm just going to write the definition, 8x plus 1. So this says, hey, you multiply your input by 8, and then you add 1 to it, right? You add 1 to it. You don't add 8 to it. Add 1 more. And you want that to become 17. If I subtract 1 from each side, I've got 8x is 16. And if I divide both sides by 2, I get x is 16/8, which, of course, is just the number 2. So for 3b, we're looking at the value of 2. Moving on to question 4, we have 4 beautiful monomials that involve exponents and division and multiplication, power to powers, and we're asked to simplify these. When we come up with these simplified expressions, right, we understand that we cannot have negative exponents in our answers, and no fractions within fractions, no mixing of decimals and fractions. This first problem, there's just one thing, right? We just have to combine these two. And if I look at this, y to the -4th means I'm dividing by y 4 times, and then I'm multiplying by y 6 times. And if I visualize that, it's like heat. I'm dividing by y, 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 y. But I'm multiplying by 6 of them. Y, 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 y. So if I look at this, right, there's a giant 1 there, and I'm just left with 2 factors of y. Shortcut, of course, is that negative 4 plus 6 is 2, right? We're left with y squared. So my answer for this is going to be 6x to the 5th power times y to the 2nd power. And I can see that's quite simple. Next problem. All right, this one, I'm going to go ahead and write down, I'll do this the way that we discussed these initially in the class. So I know that the number 21 is 7 times 3, right? And I'll write this 7 in the denominator that I already had. I can see that I have the least factors of x in the denominator. So I'm just going to write x to the 8th power in the denominator, and I'm going to mirror that in the numerator. And I need exactly 2 more factors of x in the numerator so that that equals x to the 10th. So if I'm looking at this right now, right, that's 8 factors of x times 2 more factors of x, which is going to be 10 factors of our friend x. So looking at this now, right, it's very clear to see that there are some quote-unquote giant 1s. There's a 1 in the form of 7 over 7. That's gone. And there's a 1 in the form of x to the 8th over x to the 8th. That's also gone. So we're just left with a factor of 3 and then 2 factors of x. A factor of 3 and 2 factors of x. That means our answer is going to be 3. Oops, in line B, it's going to be 3xx or 3x squared. I should write this over here. 6x to the 5th and y to the 2nd. All right, let's move on to part C. Here's C. Okay, this is fun. So I look at it, it's just multiplication, right? And if I want, because of the commutative property of multiplication, I'm free to reorder this. So I'm just going to point out that this is a 4 times another 4 times another 4 times 3 of these x squareds, 2 and 3. Well, when I multiply 4 times 4, I get 16. And 16 times 4 ends up being the number 64. Is that right? Is that right? 16 times 4 is the number 64. Yeah. And also 4 to the 3rd power is 64. Yeah, that's correct. And then if I look at my factors of x, right, there's 2 factors of x here, and then 2 more factors of x and 2 more factors of x, meaning I'm multiplying by this number, this variable x, 6 times. There's 6 copies or 6 factors of x. So for line C, we'll write 64 x to the 6th, 64, and then 6 factors of x, x to the 6th power. Last question is part D in this group. And the temptation is to look at this and say, oh, that's just 2, right? The problem is this thing in the denominator is not x to the 5th, it's x to the negative 5th, meaning this is not a giant 1, right? This isn't x to the 5th over x to the 5th. It's x to the 5th over x to the negative 5th. So the nicest way to deal with negative exponents is to just get rid of them. So I'm going to multiply this fraction by the number 1. Why can I do that? It's the identity element for multiplication. You can multiply by 1 and you don't change the value of the thing, you just change its format. So I'm going to multiply the denominator by x to the 5th, because I know that when I multiply x to the negative 5th times x to the 5th, it will equal 1. And when I do that, I also have to multiply the numerator by x to the 5th. So what I'm multiplying by is 1. All right, so big idea right here. These two things, when I multiply them together, that's x to the 0 power, and x to the 0 power equals just the number 1. Another way to think about this, if you take any number, I don't care what it is, like the number 5, and if I go divide by 3, divide by 3, divide by 3, and then I go multiply by 3, multiply by 3, multiply by 3. Look, 5 divided by 3 factors of 3 and then multiplied by 3 factors of 3 is going to be exactly, surprise, right, 5. So I can see that I've got like the number 1 down there. I divide by x 5 times, and then I multiply by x 5 times. What do I get? I just get the number 1. So there's a giant 1 in the denominator. And what's in my numerator? 2 times x to the 10th, right? 2 x to the 10th power. There are 5 factors of x and 5 more factors of x for a total of 10 factors of x. So let's write that in our answer line. 2x to the 10th. 2x to the 10th power. All right, moving on. Solve each equation below for the given variable. What a mess, not a mess. Look, if I've got x plus another x, that's just 3 x's plus a 5 equals 2x plus 20. I'll subtract 2x from each side. If I take away 2x from the left, it becomes x plus 5. And of course, I take away the 2x from the right, that becomes 20. Always pause and say, hey, what did I do? I just took away 2 x's from each of the sides, right? 2 x's from the left, 2 x's from the right. Now I'm going to take away 5 from both sides. Take a y, an x5 rather, away from the left, it becomes just plain old x. Take a 5 away from the right, it becomes the number 15. So 15 is the value of x that makes this true. Not really a problem that we need to check. I think we know that we're correct. However, it is nice to just review the procedure for a nice tool for checking. So if I take the value 15 and store that as x, I can compare the left and the right hand side and make sure they're the same. So on the left hand side, I've got x plus x plus x, which is clearly 3x, but I don't want to assume I'm right there. So I'll say then plus 5 more, and I get the number, boom, 50. On the other side, I have 2 times x, or I could have just typed 2x. Let me do that. 2x, and then plus 20 more. Guess what? That's going to be 50 also. So what's happening here is that both the left-hand side and the right-hand side become 50 when x is the number 15. That's why x is 15 is the answer, right? You can see that it clearly did the right thing. So x is 15 is our answer for A. And then for B, okay. So we have some skill at simplifying this, right? If I've got x to the 4th over x to the 3rd, that's just a single factor of x plus 2 more x's, right? So that's really an x plus an x plus an x. And then plus, this is the number 11, and that equals 44. So I'm looking at 3x on this one side plus 11 is 44. So 3x is subtract 11 from both sides, 33, and then divide by 3. X is 11. So I don't know why. I feel like maybe I glitched there. So it's probably, I want to check that. So I'm going to take 11 and store that as x. Boom. And now I'm just going to compare x plus, let me enter the original problem. So a fraction, I had x to the power of 4 over x to the power of 3, okay, plus 2x, that's fun. No, I got to get out of the denominator. Sorry. Plus 2x, still fun, not as much fun. And then plus 22 halves. 22 halves. Give it to us. We're looking for the number 44, and we got 44. So clearly x is 11 is the correct value because it makes both the left-hand side and the right-hand side equal the number 11. So that is our solution to B. All right, with that, I think we're on to our last page. We said 11. X was 11. Last page. Next. Evaluate the given expressions if, and you can see I'm giving you values for A, B, and C. So I'm going to take a moment here. This pen seems a little bit too sloppy. Let me make it thinner. There we go. So I'm going to take a moment here and just set this up to receive values. So in my numerator, I've got a place for A times a place for B that's going to get squared minus the value of 16 minus a place for the number C. And then my denominator, I'm going to have 5 times a place for B. So first thing I'm going to do is I'm going to grab this value of A, which is -4, and I'm going to put it right into that spot. So as soon as I grab that A and put it there, boom, there's the number 4. Be careful, it was -4. There's the -4 right there. Next, we're going to grab this value of B. B is 2. And I got to put it 2 places, right? It's going to go both here and it's going to go right here because you can see b was squared in the numerator, and it was 5 times b in the denominator. So let's place b in. This is going to be the number 2, the number 2. And the last thing we have to grab is just this value of c. c is 12, and it's going to sit right there. So we can just place it there. So I'll do this old school. That's going to be negative 4 times a positive 4, which is going to be a negative 16, minus another 16, minus the number 12. And I'm going to be dividing whatever that is by 10. So 16 and 16 is 32. And if I take away another 12, it's going to be the number 44. So 44 over 10 is our answer. 44 over 10. That does reduce to, what, 22 fifths? That would be a fine version. We could make that a decimal also. I'm going to evaluate this on the calculator just because I like a little confirmation. So open parens, here's the negative. Oh, let me grab a fraction key first. So numerator. I've got open paren negative 4, close it. I'm going to be multiplying that by 2 to the, oops, I would feel better squaring it outside of it. 2 to the second power, and then I'm going to subtract 16, and then I'm going to subtract the number 12. And in the denominator, I'm just going to look at 5 times 2, which is 10. And it tells me, yeah, oh, one big problem, though. Those were all negative. See, I'm so glad I typed this because I would have forgotten that it's negative 22 fifths. And if I want to see that as a decimal, I can hit this button on my calculator, and it says, oh, that's the same as negative 4.4. So any of those would be fine answers. You can say negative 44 tenths, negative 22 fifths, or negative 4.4. All of those work. I'll put negative 4.4. And then this one, we're going to take the value of A. We're going to square that plus 5 times the value of B, and then we're going to subtract C. Oh, let me put parentheses for C. All right, so A was the number negative 4. Ooh, there we go, squaring that negative again. And then B is 2. I'll place a 2 for B. And C was a 12. So I'm looking at 16 plus 10 more minus 12. That looks like 26 minus 12, which is the number, which is the number 14. 14. So we should be getting 14 there. Again, I'm looking for a confirmation. So I'm going to go negative 4, and I'm going to square that. That's that 16. And then plus 5 times 2. There's that plus 10. And then minus the number 12. And you can see, look at, in all of its glory, there's our friend 14. All right. Second to the last problem. Mr. Roberts and Mr. Woolard are racing their bicycles on the Shasta High track. They're souped up bikes. They go fast. Because Mr. Roberts is clearly older and slower, he was given a head start of 4 meters. It's not cheating if you're old. And he travels at a speed of 3 meters every 2 seconds. Okay. That's everything, right? So a head start, that's my y-intercept. Y-intercept is 4. And you can see my speed is 3 meters every 2 seconds. So my equation is y equals 3 over 2 times x plus a head start of 4. I'm going to go ahead and graph that one at the same time. So here's the head start. At time 0, I'm 4 meters down the track already, thus a head start. And then I go 3 meters, 1, 2, 3 in 2 seconds, right? 3 meters every 2 seconds, 1, 2, 3, 1, 2. And then 1, 2, 3, 1, 2, somewhere up here. So I can grab this, and I'll model this with a line. That's great. So this is the equation that models my race. And honestly, if the race was only 7 meters, I probably could win Woolard. I don't know. Now, Woolard does this thing where he does not pedal for the first 3 seconds. So on your mark, get set, go. He stands still, and he doesn't start moving until right here, right there. At that, by the way, if we were to talk about that point, that's the point where x is 3 and y is 0. So we can think about that very clearly. X is 3, y is 0. Meaning he hasn't gone down the track. He's sitting right there at 0, but 3 seconds have elapsed. Now, he travels at a speed of 5 meters per second. So I go up 1, 2, 3, 4, 5 over 1 second. There we go. 1, 2, 3, 4, 5 over 1 second. You can still see I'm in the lead, right? However, I'm about to lose. So I'll go ahead and draw that line. There we go. Perfect. And that is the line that models Mr. Woolard's race. Now, we know his slope, right? We know that his speed is equal to 5 meters per second, or just 5 meters per second. However, we do not know his y-intercept. And if we look at this graph, right, his y-intercept is clearly, I'll grab this color, maybe I can. His y-intercept is clearly somewhere, whoops. Oh, it's not become a straight line for me. Anyways, it's somewhere way the heck down where, I don't know. It's down there somewhere. We got to figure out what his y-intercept is. So, hey, we just spent a bunch of time talking about this on the very first problem, so let's just use it, right? We know that this is not a vertical line, so we can write it in the format y is mx plus b. We know m is the number 5, and we also have a point, right? It turns out that this point where x is 3 and y is 0 and y is 0, right? X is 3 and y is 0 is a total legit point that we know exists on the graph because he doesn't move for 3 seconds. At 3 seconds, he starts moving. At 3 seconds, he's 0 meters from the starting line at that moment. So we can say y, which is 0, equals 5 times 3 plus b. Take that equation a step further, and it's 0 equals 15 plus b. And if I take away 15 from both sides, I got negative 15 is what b is. So we now know that y-intercept, and we knew it was down further, right? Because of the negative numbers down here somewhere. Well, that down here somewhere is like at the number negative 15. So we can get that even without the graph. So we can write his equation. Woolard's is traveling at y equals 5 meters per second, so 5x, and then minus 15. So we could have done two things, right? If he wanted, he could say, hey, instead of just sitting still for 3 seconds, he could have started 15 meters at the back and made it. Now, it looks like if the race is 12 meters long, it's a tie, right? It's a tie. If the race is 10 meters long, I'm the winner, right? Anything after 12 seconds, Woolard is in the lead, right? Woolard is the winner. All right, final question. Let's just make sure we can see all those answers. Final question involves our friend the Jabberwock, right? We're looking at dimensional analysis, and it's a pretty straightforward problem. There is a giant one that I talked about in class, and again, if there's giant ones that you're not sure about, I'm happy to write those on the board on test day. But I think anything that you need, I will already have written on the board, any values of 1. The important idea is that how do I make things go away by using equivalent values in multiplication? So I don't know why it says 12 feet per 1 seco, but I don't know why there's an O there. But he's traveling, Miss Fifield rather than another name, she's traveling at 12 feet per 1 second. And we want to know what her speed is in miles per hour, and we're going to do that using giant ones. Now, that's our goal. When we're finished with all this, we want to see miles in the numerator, miles, and we want to see hours in our denominator. So first things first, let's get seconds to go away, right? So I want seconds to go away, and they're in the denominator, so I'm going to place seconds in the numerator. And I'm going to put a giant 1 value that I know here. I know that 60 seconds is equivalent to 1 minute. That's the same amount of time. That's why that's equal to the number 1, right? 60 seconds, 1 minute, it's 1. I could multiply by the number 1. Now I'm going to take that 1 and I'm going to multiply by another 1 that I know. I want here minutes to go away, right? So the seconds are already gone. In fact, I can cross those out if I want because I've got these units seconds in the numerator and seconds in the denominator. I'm now looking at feet per minute, right? That's what this is. Whatever the number is, it's feet per minute. I want the minutes to go away. They're in the denominator, so to make them go away, I'm going to place minutes in the numerator, right? So you can see they were in the denominator. I'm placing them in the numerator. And I know a giant 1 that involves our target, hours, and minutes, and that is that 60 minutes is the same amount of time as 1 hour. It equals the number 1, so you could multiply by doesn't change anything. So we've got this, and I'm going to go ahead and now I can eliminate the units. The minutes are gone with the minutes. And what are we looking at now? We are now looking at our friend feet per hour. Last giant one that we need to multiply this by, and this was one that was on the board. It turns out that 1 foot, well, not 1 foot, 1 mile is the same thing as 5,280 feet, 5,280. So I've got feet in the numerator right now. And if I want the feet that are in the numerator to cancel, I need to place feet down here in my denominator. So I'm going to place feet in the denominator, feet, and I'm going to put 1 mile in the numerator. And I know the following: 1 mile is the same, I'll say it again, 5,280. 5,280 feet in 1 mile. So taking a final look at this thing, right, you can see that this is great. I've got feet in the denominator. Those are going to cancel with the units feet in the numerator. So the only units that I have left in the entire problem in the top is miles, and in the denominator I have hours. So whatever this number is, it's miles per hour. Now, what's the number? Okay, so in the top there's the number 12, and I have to multiply that by 60, and I have to multiply that by another 60. And in the denominator there's 5,280, 5,280. That is her speed in miles per hour. I just need to know what that number is. Turns out I've got a friend that's going to help me with that. Get over here. Come on. There it is. And I'll hit clear. I'll grab a fraction template. And in the top, I'm going to go 12 times 60 times 60. And in the denominator, I'm going to place 5,280. 5,280. And I press enter. And there it is as a fraction. However, I don't think about speeds. Officer, I was only going 90/11 mile per hour. No. Let's hit this. So it says 8 point, if I round it to the nearest 2 decimal places, 8.2. So speed is what? 8.2. What are those? Are those gallons of milk per refrigerator? Are they daisies in the field? Or are they cows eating clover? No. It's 8.2 miles traveled per each hour. Miles per hour. So that is the answer. And that's how we get the answer, by starting with the given speed in feet per second and then using 3 giant ones. Again, the idea of a giant one is any distance or amount of time divided by itself is equal even if the units are different. And the beauty of that is that's a great way to go from one set of units to another. All right, class, that's right about 38 minutes. I hope you use this to your best ability to prepare for your test this week. I hope you do well. And I'm looking forward to grading a lot of A's. You're going to have a lot of A's and a lot of B's, right? Get a lot of good grades. Study hard, and I'll talk to you later. Goodbye.